All right, welcome back, everyone. People who are online, can you hear me? Okay, thank you, Connor. Thank you, Mason. Okay, so let's get started. Can we close the door, please? So much distraction. Okay, so until now we have discussed supervised learning and we have discussed unsupervised learning. And today we are discussing a completely different paradigm of learning that's known as reinforcement learning. So like high level, we are not looking for any classifiers. We are not looking for any particular pattern given some data set, but rather we are trying to optimize something here, right? So that's the high level idea of reinforcement learning. And what we are doing is we are trying to map some situations to some actions so that we can maximize some quantity. And in like all of the cases almost, we are trying to maximize a reward. Now, a reinforcement learning, as I said, is a different paradigm of learning. It's neither like supervised, neither unsupervised. It's more like an optimization process. But in addition to like a given optimization problem is like you're given some values, you're given some variables, and you're trying to optimize over some feasible space. But here we are trying to look into the future in some ways, and then trying to optimize our future like steps or future actions. And that's the learning part. That's what like my agent is going to learn in this like reinforcement learning. So let's look at like the specific definition. And before jumping into the introduction, I just wanted to like summarize what we'll be doing today. So there is this introduction to reinforcement learning. We'll look at some examples where reinforcement learning has been successfully applied. And then we'll try to understand what are some important elements of reinforcement learning, like given any problem, those are the elements that will exist always. And so we should be familiar with those terms and we'll understand what those terms are. And then finally, we'll try to understand what's the Markov decision process. And reason being that there are a few known ways of modeling a reinforcement learning problem. And one of the very popular or one of the very common ones is the MDP or the Markov decision process. And that's why we want to understand that. I'm sure you might have come across like a Markov process in general or like what a Markov process is. And we'll try to build on that. Thank you. Yeah. So going back to the formal definition, and before like even we like jump into the introduction and examples and everything, I'd just like quickly like to point to the source at the end. So this is nothing but a book, and it's a very good book, and I've like derived all my content from there. So just in case you want to dig deeper into reinforcement learning, just go to this like source link, and that will lead you to like a textbook on reinforcement learning. So just wanted to point that out. All right, so coming back to the definition, as I said, it's a closed loop type problem. So what's actually happening is that there is an agent and there is an environment. And the agent has a goal that this agent is trying to achieve within that environment. And obviously, like the agent has some information of that environment, right? And based on that, this agent is taking some actions maybe or like interacting in some ways with the environment. And it's trying to optimize some ways. It's trying to take the best course of action to maximize its goal, whatever that goal is, right? So the fact that it's known as this like closed loop process is because of something like this. If, so as I said, you have like an agent. This is how we model these problems, right? And then you have this environment, which in some papers you will see is known as like the world. That's what they call it. So we have the environment, and there is some interaction between the agent and the environment, right? So the agent interacts with the environment. So basically takes some action to interact with the environment, right? But then the environment in turn gives it like some sort of update, right? So that update is sometimes known as a state update, right? So the state of my agent changes. So like imagine a robot like moving in some space, right? So the goal of the robot is to like maybe pick up some trash, right? So then it's moving towards, so the environment is like this room, for example. And so the robot is actually moving in the environment. and it does some action. So it picks up the trash, right? And then the environment gives it like some kind of like a reward that it did the right thing. So it moved towards its goal, right? So it updates the state and gives it some reward. Right, so this is the high level reinforcement learning process, and the agent in this entire like closed loop process learns to optimize its like actions. And obviously we'll talk about more like details how it does that. But that's the fundamental idea behind reinforcement learning, that the agent needs to learn the best course of action in order to maximize its reward. And so because we are trying to maximize our reward through some actions, right? This is largely an optimization problem that we need to solve. And of course, we won't be solving this problem. As I said, today we will just be formulating the problem and trying to understand different terms. And then we'll try to understand the Markov decision process. And next time, we'll see how we can solve this. Okay, so that's what the formal definition talks about. It's a reward-driven trial and error process in which a system, or as I said, an agent, and we'll be calling that interacting system as an agent, right, learns to interact with a complex environment to achieve rewarding outcomes. And that's what reinforcement learning is. Now, the trial and error process is that your agent has choices, right? If you think about a robot vacuum, it can move like straight, it can take a left, it can take a right. So it has like certain choices to make. And then based on those choices, it decides its course of action. And in some ways, we would like that agent to be able to look into the future somehow or make certain decisions so that the reward it's getting is maximized. So that's a difficult problem to solve. If you think about it, I don't know what's like. Let's say I took some action which gave me an instant reward. Let's say like, okay, so there's some trash up there, and if my like vacuum moves there, it gets instant reward. But let's say there was more trash up there and it never tried to take the action to go towards the right. So in like some distant future, it missed more reward to get like an instant reward. So then if you think about the problem to optimize in some future time steps, that's a hard problem. And it's like hard to learn, right? And so that's why reinforcement learning is hard, but obviously there are ways to get away with it and like to actually model it and to actually get very close to the optimal solution. And we get like really good results when we are able to model this agent environment interaction. All right. So reinforcement learning can be a gateway to the quest for creating truly intelligent agents. And there are some examples we'll be looking at today to better understand the power of this process of agent learning in the environment and interacting with the environment and learning something from it, right? So as I said, so this is the core idea of reinforcement learning. The agent must have goals related to the state of the environment, right? So for example, in my vacuum case, my goal is to collect as much trash as possible, given an environment, which is a room in this case, all right? But in their simplest possible forms, like without trivializing any of these things, like the sensation, the action, and the goal, meaning I would like to encompass as much as I can in the definition of my action, my goal, and my reward. Of course, I cannot take into account everything. And maybe a lot of things, for example, the room has like a laptop here, or the room has a board here. All this information is not useful for the vacuum, robot vacuum. Maybe that's not useful. So I shouldn't be modeling that. But then it's important that there are like these seats in between, and the movement of my vacuum will be controlled by how these seats are positioned. So maybe that information is important. Right, so that's what this is talking about. All right, I think I saw somebody posting something in the chat. Okay, sorry, I thought there was a question. Okay, so before we jump into the like different elements of reinforcement learning, let's look at some examples where reinforcement learning has already been used. And I'm pretty sure you must have heard about the AlphaGo that was able to defeat the world #1 player, right? And so there is something called AlphaGo 0, which is like completely trained on like a reinforcement learning model. And that was able to even like beat AlphaGo after like being trained after like 40 days of training. So that's like one application, one example, and that's showing. And so there are certain like types of problems where reinforcement learning works better than like other forms of learning. That's also the case. For example, in like game type situations where like, of course, you're going to have like certain set of rules, and we'll see that they're not like as easy to learn. It's not like you can just like list down all the rules and like make some kind of a rule-based process, because there is this like whole uh, set of implications that might happen given your action, right? So it's not that like if this has, so you have like a whole list of like if else statements, and then you're playing a video game and you just like decide to create like this entire decision process wherein you have as many if else as possible. But then looking at the number of decisions that are possible, this becomes enormous. And that's why we resort to reinforcement learning. Okay, so that's one example. In engineering, specifically, I would say in recommender systems, that is like a very, like there's a huge surge in the number of applications. For example, if you're interested, you should go and read this Horizon, which is an open source reinforcement learning platform that was developed by Facebook. And they are using that to make recommendations better. And why it's like reinforcement learning has a good application recommenders, because recommender systems, because here we are trying to in some ways predict how a particular customer or a particular user is going to act based on certain variables, right? So then this link that I've provided will lead to an article that talks in detail about what this Horizon is. So that's another very good, I would say, application of reinforcement learning. In healthcare systems, there is again a surge in using reinforcement learning instead of utilizing supervised or unsupervised related techniques, because without having a lot of data, let's say you have some policy. So we'll come to that. A policy is something that maps your actions to your state. So basically, based on some policy or some rule, your agent acts and then takes some action, right? So you can develop those policies based on some information about some disease. And then you don't need the entire data for like all the processes that are related to maybe that disease. So then that makes your life easier in healthcare. So a lot of applications like are switching to reinforcement learning in healthcare as well. And one of the very famous like robotics is one area where you see a lot of like reinforcement learning happening. Learning-based robots are used to perform specific tasks, and like one very well-known example is this AI agent by DeepMind that is used for like Google data centers. So again, like I have provided a link. You can go and check this one, or you can just like go ahead and Google this. So this is a very well-known application of reinforcement learning. So having said that, like we know that reinforcement learning is actually achieving really good results, and you don't need a lot of, you don't need data. And in some applications, that's like really good, because sometimes it's like really hard to collect a lot of data. I mean, of course, you need some information about the process and other things, but not as much data as you might need in other supervised or unsupervised learning problems. So that's like one of the reasons of why this is becoming really popular. The other reason is that if we look at how humans learn, right? We learn through experiences. For example, like look at a child who has never come across like a hot cup of coffee, and when they touch that, they know that this is hot, and they shouldn't be like it hurts them, right? So they shouldn't be touching that. So in some ways, this reward versus penalty-based system is something that stimulates humans to learn from their environment. So it's biologically inspired as well. Like we are not necessarily given some data to prove that this cup of coffee is hot and we shouldn't be touching it, right? So we learn from experience, and that's what in reinforcement learning and agent is doing. Learning from experience, definitely initially you'll have some like really bad actions, but like after certain iterations in that closed loop form, you will get to that point wherein you start making good decisions, right? So that's the fundamental idea. And there are some examples that you'll always come across when you're like reading any paper or any reinforcement learning related application. And because like the early development of reinforcement learning actually was inspired by these different problems. And so that's why I just like wanted to list a few of them, not all of them. So for example, like if two players are playing chess, right? And so when you're like the next move, when you decide your next move, you're not just thinking about your immediate uh, move and the immediate reward that you're going to get out of that move. But in some ways, you're also building that strategy of like what might happen after a couple of moves, right? So you're taking both the immediate reward and what might happen down the line type of goal into account in order to win your game, right? So that's like anticipating possible replies and counter replies, right? And by immediate intuitive judgment, and then putting both of them together is important if you want to win that game of chess, right? So that's like one motivation behind developing these reinforcement learning systems, because when an agent is interacting with an environment, let's say you're playing a game, you're not just looking at your immediate what you're going to get out of it, but you're also looking at whether you're going to whether you'll be able to win the game or not, right? So that's like one example. Then there is this another example, and again, I've like derived this from the textbook. An adaptive controller adjusts the parameters of, let's say, a refinery. So you're having two trade-offs, like you want to maximize your yield, you want to minimize your cost. And so there is this like quality and cost trade-off. And without sticking to the originally set cost or yield or like whatever parameters for the controller, if the controller adapts based on like the way it interacts with the environment and based on the result it gets, the immediate benefits that it's getting versus the long-term cost benefits it's getting, then this like calls for a reinforcement learning application, right? So that's one. And then a mobile robot, people have actually implemented reinforcement learning models for robots. So for example, a mobile robot should decide whether it should enter a new room in search of like more trash. Let's say like we're talking about a vacuum robot, or should it like go back, find its way back to its battery recharging system because maybe it's like getting low on battery, right? So it makes its decision. This robot will make its decision based on the current level of its charge, right? Whether it has enough charge that will be able to move around and carry more trash, or like how quickly and easily it will be able to find the recharger if it goes inside the room and starts collecting trash. So there are two things that you're like weighing in. Like, is there an immediate benefit? Let's say your battery is low, but you still decided to go inside and get some trash, but then your battery died in the process. Of course, you collected trash. What was the long-term goal? Was the long-term goal to clean up the entire house? Then maybe you didn't achieve that because you were just able to clean up a room. And if it was like the long-term goal of cleaning the entire house, and it might have waited, like the time is not an issue, it must have gone back and like charged itself or recharged itself up to a high value and then come back and collect the trash. So all those like trade-offs that exist in real-world problems should be taken into account when this agent is learning and making decisions, because every decision that the agent makes in some ways it impacts the decision that it'll take like later or make later. Okay, so I'm sure like the idea of reinforcement learning is clear to everyone. What exactly we're doing: agent interacting with the environment and making some decisions, trying to achieve a goal, maximize the value or the rewards, right? And we are going to like mathematically understand what these terms are one by one, but like understand the high level idea for now, right? And so these are some good examples that we just looked at. Now, to summarize reinforcement learning and its elements, there are like very concisely speaking, there are four important elements. So as I said initially, we are doing optimization. We are not finding a decision boundary. We are not clustering anything. We are not clustering data. We are optimizing something, right? So my goal is to find an optimal way of making my decisions and my strategy. So that's the first element of any reinforcement learning problem. Okay. The second important aspect of reinforcement learning is delayed consequences, right? We just saw that like let's say in a game of chess, my current decision can impact my later outcome, right? So my challenge is that I do not immediately see the outcome of a decision, right? And maybe I took a certain, so like in terms of what should an agent be doing to maximize their like outcome? Well, there are two choices. It might want to explore or it might want to exploit. So there is a trade-off between explore and exploit. Meaning if you go and like keep exploring, maybe the immediate reward that you were getting gets lower as you start to explore. Or maybe you wanted to exploit that immediate reward and you didn't want to go like later in time and look for other rewards, right? So there is a trade-off that exists. Like agent has to make decisions by learning about the environment, and it's only able to get a reward or a penalty based on the decisions made. So in some ways, let's say I made a decision. Let's say I had like choice of selecting one thing out of two, and I selected one. In some ways, I never got like the ideas. So I never got the experience of the other choice that I had. So in some ways, my learning process is kind of becomes myopic in the sense that I never knew what the rest of the data had in store for me. And so I just learned based on the current decision that I made. So that's the trade-off here again, that I did not learn from like all possible options, right? I just learned from the decision that I made, the choice that I made. So so that's the example. For instance, the agent is unaware what would happen if they opted for a different option. Like I'm not aware of that, right? So I need to learn from my choices or the decision that I made. Okay. And then finally, because this is a learning model, right? We would like it to generalize. So we developed something that's known as a decision policy in the course of like defining a reinforcement learning problem. So what is a decision policy? Well, a decision policy is something that maps the actions of the agent to a particular state. State meaning what, like where exactly you are in the environment. So obviously, if you are like, for example, think of the robot, it's at a particular coordinate in your room, and then based on its action, it moves somewhere else. So the state changes that way, right? And maybe my decision policy was that you just keep moving straight. That was my decision policy. So it just like keeps moving and its state keeps changing, right? So decision policy is to map from past experience and convert that to some action, right? So I have to take into account my past experiences and then convert them to action. So I can like lay down some rules, and that goes back to the initial discussion that I just had. That like if I have this set of rules already created for my uh, agent and I'm not letting it learn from the actions, then the issue is going to be that this might become an enormous problem for real world problems, right? How many rules can I just list down? There are just like too many in real world, right? Because like think of the self-driving car. So self-driving car is a good example of like reinforcement learning. Of course, I can lay down all the rules, like if a road looks like this, do this versus this. But how many? There are so many unknowns. There is like a whole distribution of values, and that's exactly what we encompass in our model. That we have to think of this as a distribution rather than like some deterministic values out there, and we are doing an if-else kind of a solution to this. All right. So this was a high-level overview of what reinforcement learning is. We are going to go into something that's known as the Markov decision process, and we'll understand how we can formulate a reinforcement learning problem using Markov decision process. But before that, I quickly wanted to go into like the differences of reinforcement learning as compared to other forms of learning. So if we can define reinforcement learning using optimization, delayed consequences, exploration versus exploitation, or just exploration, right? And then generalization. Then if I think about supervised learning does not involve exploration and delayed consequences. If we go back into the idea of supervised learning, I already have this set of experiences. I have a data set, right? And once I have the data set, I also have the results of that data set, right? And I'm trying to find a function that could have mapped my input to my output. Right? So like given some like apple or orange and given some pictures of apple, you're trying to find out whether this like new fruit is an apple or not, right? And that's what supervised learning is. Then in unsupervised learning, you're trying to determine some patterns in your data. Again, it does not involve exploration or delayed consequences because you already have some model. And then if a new data point comes in, you just want to know where does it lie with respect to the existing model. Where, like in which cluster does it lie? How much far away is it from an existing cluster and so on. So you're not doing any exploration, unlike reinforcement learning where you're agent is doing some exploration in terms of like taking actions and learning from that. And there are no delayed consequences. Like if I'm trying to classify a fruit, and it is obviously going to go near the cluster of apples, and so I know that this is an apple, right? But if we think about if we think about reinforcement learning, we have this like goal-directed learning and decision making. We are continuously making decisions, which we never do in any of the other paradigms of learning. We are making decisions because we want to reach some goal, and we want to maximize the value we derive from like this set of decisions that we make. All right. Okay. So any questions before we jump into sequential decision making under uncertainty? Yeah, this is just like a high level definition of reinforcement learning. People who are online, any questions so far? Okay, that's fine. Let's move on to sequential decision making under uncertainty. So obviously, in most of the real world problems that we want to solve with reinforcement learning, there is some uncertainty involved. For example, my robot vacuum moves in like some environment, which is this room. And there is some uncertainty in like how it's going to get rewards in the future. I don't know the entire like course of like actions and the rewards that it might get based off of its actions, right? So that's why what we do is we try to model this process involving some uncertainty. And I'll come to that we use something that's known as Markov assumption or Markov property. I'm sure you might have come across this term before. And we utilize that to learn, to model reinforcement learning. Okay. So one quick example of like any reinforcement learning system could be a student tutor, so an artificial tutor. Let's say we want to build an artificial tutor on some platform, and so the tutor is going to be the agent, right? And the student is going to be my environment, okay? So what the agent is going to get like a +1, so that's the numeric reward it's going to get if the student gets the problem right, and a -1 if they get it wrong. And in the process, the action that the agent or the teacher is taking is that they're teaching them something, right? They're teaching them some concept, and then they're asking them to solve a problem. Okay, so that's how that's like a high-level description of what like a reinforcement learning system could look like, right? So you're continuously getting rewards. Now, one thing that we have to remember, one downside of this could be that the agent might learn to give easy problems because the student always gets like a +1, and so that's how they'll get a reward always, right? So what this example is pointing to is that we should have a correct definition of how the tutor is deriving value from this process, not just like this instant reward that the tutor is getting by making the student like giving the student some easy problems to do, and they get it correct always, right? So there are other aspects to it, and so obviously those aspects are important when we are modeling this problem. This is not like an optimal solution that you keep giving the student easy problems and obviously they're able to do them, and that doesn't really show whether they learned or not, right? So what we do is we do some kind of a sequential decision making a model, right? So there are time steps. So every time an agent takes an action, that's in some time step t, right? So that's how we are going to denote that. And at every time step t, an agent can take an action a sub t. And then what happens is, remember the closed loop that we had, right? So the moment the agent takes an action, based on that action, the environment is going to make some updates. So those updates could be that the state of my agent gets updated. Maybe my robot moves a step, right? And then it gets some reward. So maybe it picked up some trash, so it got some reward, right? So just remember this closed loop, and it'll be easy to visualize what's going on. In time step like t, my agent took action a sub t, environment updated that action, emits some observation. Observation is known as state. So I'm like first calling it some observation, meaning maybe some change happened in my agent, maybe nothing happened, right? So let's call it observation, and that's O sub t. And it got some reward, R sub t, right? So then agent receives this observation and reward. Okay. So now, obviously, this is not just like one step. there are going to be a lot of steps, right? And so we can consider a sequence of like a lot of past observations and actions of all the rewards and create some history. Because you can tell, like in any problem, that history is important because that history impacts like what next step you should be taking, right? So this is how so history is nothing but a sequence of AOR, so action, observation, reward, action, observation, reward in every time step, right? Now, I've been like calling this particular term state, right? When an agent moves from one time step to another, I'm calling it state. And it's denoted by S sub T, right? So now here is the formal definition of a state. A state is nothing but a function of all the history that I have, right? So a state is essentially a function of all these steps that the agent took and it received from the environment, right? So that's why the state is like a function of H sub T. All right. Now, if we think about it, like if we keep a track of this history of almost all the actions that are there and all the rewards that this agent received, it will become like a tedious process. And if you think about it, like the amount of data that I have to gather and make my decision based on that, then it defeats the purpose of like making this decision faster and making it more efficient, because then I'll be carrying this whole load of data of like all the historical decisions that I took. And in some ways, this is justified that we want to get rid of some of this history. And the reason being we want to get rid of some of this history is because think of humans. Like when I was a child, I learned certain things, but a lot of those I don't like want to keep them in my memory all the time. Based off of those, I've made some other decisions and learned something else that is there in my memory, but not quite what I started with, right? I don't like, even humans, they don't keep everything in order to make every decision. We just somehow learned and updated my state, my current state, or my state from like the past few days or maybe the past few years, but I don't remember what I did as a child, like not everything, right? So then even when these systems are biologically inspired, that makes some sense that I don't have to carry all this history all the time, because a lot of it is not even impacting my current decisions. So that's the fundamental idea that is utilized when we think of this Markov assumption or Markov property. Okay, so what is this? Now, first of all, real environment can have like more information that is hidden from the agent. So we don't care about that while modeling this process because maybe we don't need that. Or maybe we need that, but there was no way to capture that. And so obviously we're going to miss on that. But this is what we have to live with, right? So that's there. And yeah, so that's that. And then coming back to this history, like how much history do we need? So in order to model that history or that state, because state is a function of my history, right? What I'm doing is I'm using something that's known as Markov assumption. And this Markov assumption or Markov property, it refers to the memoryless property of a stochastic process. Now, if you think about like what's happening in my history is that there's an action, observation, reward, action, observation, reward, right? But then not everything is known. And so there is some stochasticity usually in a real world. And so it's a stochastic process. And so we can model it as like a Markov process. And what a Markov process is, and like anybody is familiar with Markov process? Come across that word at all? You must have heard that word, right? But not remember. Okay. So one easy, yeah, sure, Sean, I know you must be knowing it because, yeah, Markov probability, right? Okay, intro to AI. So people who've taken AI courses must have come across that. But let's like quickly remind you what it is. It refers to the memoryless property of a stochastic process. So basically what it means is that like your future states, they do not depend on your past given your present. So that's how you model these stochastic processes, right? And that's like one efficient way of modeling this history that is impacting your state. So basically, you're saying that this entire history is nothing but this state at time step t. because this h sub t is actually encompassing all these things, starting from time step 1. But if I make this assumption that my processes or my steps in my learning process are a Markov process, right? Then I can safely say that this is like memoryless in the sense that my future states, they do not depend on my past. They just depend on what I'm doing now. And that has shown like really good results, and we'll see why and how. So a few things to know when we start discussing this Markov process or Markov property is that there is a transition that's happening with the agent. So let me like quickly write that down here. Okay. So first of all, like we talked about history. So my state for any time step t is a function of my history, right? And then my agent is moving from one state to another. As they take some action, the environment makes them move to another state. So just remember that. So basically what I have is like state 1 goes to state 2. This is how my agent is moving. My environment is updating the state of my agent, right? So that's something that we need to remember. And okay, so this like movement from one state to another is known as transition, right? So whenever I'm talking about transition in reinforcement learning, I'm basically talking about my agent moving from one state to another, right? Now, state could be like change in some variables in the environment or change in some variables in the way I'm defining my agent. It could be anything, right? It depends, but usually it's the change in some variables that define the environment. Okay. The other is this transition probability. Okay, this is a stochastic process as I'm moving from one state to another, right? So I move from one state to another with some probability, right? And so that is known as, it's a conditional probability. So basically you say probability of moving from state 1 given, probability of moving to state 2 given I'm in state 1. Probability of moving in state 3 given I'm in state 2 and so on, right? So that's a transition probability. Like either it's known from my domain knowledge, either it's known from some experiments, or based on the information that I have of my environment, I calculate it, right? So for example, like if my robot is moving in this room, what is the probability of my robot picking some piece of trash or not? And then based on some information about this room and the way this robot has like been used in experiments being conducted, maybe I have some information about it. And so I can compute that transition probability, right? So that's that. And then like coming back to what is Markov property and how do we mathematically represent it, right? So any stochastic process has a Markov property if the conditional probability distribution of future states of the process depends only on the present state, right? So that's why it's known as memoryless, because I just like erase all the memory of my previous states. My present state decides what my future is going to be. And it's actually quite useful in a lot of like applications. For example, like in healthcare, if you're to decide the medicine for some hypertension patient, they have high blood pressure right now, and so maybe I need to give them some medicine based on their current state, and I'm looking whether they had blood pressure earlier or not, right? So those kind of things. So that's how we model this thing. And like a process with this property is known to be Markovian or Markov process. And the most famous application of Markov process is Markov chain, where you're moving from one state to another, and every state is like in the chain follows that property, right? So then coming back to our state definition, right? The way we can model this like transition from one state to another is that we are saying state S sub t is Markov if and only if the probability of this S sub t plus 1 given states S sub t and action A sub t is equal to this probability given my history and my action. So basically what I've done here is I've just like removed this. Like if you think about the entire process that my agent reached some time step t plus 1, right? My agent reached some time step t plus 1. And it moved to that based on all the steps that were involved in my history, right? But because I'm assuming that there is a Markov process in every state transition, I'm just like removing this h sub t and I'm saying it's dependent only like on my current state, that's my S sub t. That's all I did. Like just remove this H sub t with my S sub t. That's it. And so it's going to make our life like really easier, right? We can, and as I said, we can always satisfy this property by assuming that my current state is my entire history, right? So in some ways, what I'm assuming with this Markov process or this Markov property is that my most recent observation is my sufficient statistic for history, right? Because my current observation or my current state is defining my history in some ways. So it's a kind of a statistic for my entire history, right? That's what I'm assuming here. All right. So here there are some variations in the agent decision-making process. We'll come to the exact decision-making process, but I just like wanted to figure like, because we talked about observation earlier. So agent is modeling the environment as a Markov process. That's what we are doing here, right? Why do we need this Markov process? Well, we need that because my agent is modeling the environment such that my most recent observation is its current state. Right? So remember we talked about the observation that the environment gives back to my agent, right? So that is my state. Whatever observation the environment is giving back to me is my current state. Okay. Okay, so and another thing that we should not be like confused is that my agent state is not the same as my environment state. Sometimes we even sometimes we make or let the agent construct its own state. But today what we are talking about is this first variation, this one. That's it, right? So we're not talking about the second one. We are just like skipping that. That's like a more complex problem. But we are just saying that my agent is assuming that like my environment is a Markov process. Okay. All right. So what is like, where is this decision making coming in my entire reinforcement learning? Where exactly is the decision making coming in? The agent makes the decisions, right? So the decision making comes in that my agent needs to make certain decisions so that like they reach their goal and then they maximize some rewards that they're getting in like reaching that goal, right? So there are many ways of making this decision or modeling this decision process, right? There is this bandits problem that I'm going to cover in the lecture that are coming up. And then there is this Markov decision process or partially observable Markov decision process or MDP. So that's what we are looking at right now. So there are many others as well, but I'm just like focusing on this MDP or partially observable MDP. That's all we'll look at today. Because I think that that is sufficient to understand what happens in reinforcement learning. And then when we look at other variants of like modeling reinforcement learning, that'll be easier for you to understand. Okay. So, okay, so I think I discussed most of it. A few more definitions that you will see when we start deriving this Markov reward process and Markov decision process. Now, beyond the agent, we've talked about the agent and the environment a lot until now. There are a few more terms that we'll come across, and let's formally define those. Some of these you've already heard. For example, you heard what a policy is, you heard what a reward is, but now let's formally define them and then actually look at the Markov decision process. All right, so the first thing is a model. So as I said, the agent is modeling the environment. So it's the agent's like representation of how the environment is changing in response to the actions that the agent is taking, right? So that is my model. And in case of an MDP or a Markov decision process, it's simply the distribution of the next state. Because the next state, like when I move from S sub t to S sub t plus 1, right? It could be an entire distribution of actions, not just one action. So there are two things actually. There could be a deterministic next state, or there could be like a stochastic next state. Mostly we consider stochastic next state because when you're moving from state ST to ST plus 1, it could be a whole range of possibilities of actions, right? So we are considering the distribution of the actions. Okay. So it's the distribution of the next state if it's starting from some state and taking some action. And eventually we'll have a reward model that would predict the expected value of the reward when taking a particular action. Again, no need to get confused. We will actually mathematically write all those equations and then they become clear. But for now, High level model is your agent's representation of like how the environment is going to change the state, and like what all is it going to change. Okay, then coming to one of the most important term that you will see a lot throughout is policy, right? So what is a policy? Well, a policy is something that defines the agent's way of behaving in a given state, in a particular time step, right? So basically, you need policy is type of a function that maps your states to actions, right? So why, like, maybe we can think of this as like some kind of a rule wherein you have some kind of a mapping from one state to this action. If you are in this particular state, you took this action, right? Right? So roughly speaking, policy is mapped from perceived states of the environment to actions to be taken when in these states. Right? So that's why you can have the whole distribution of this. Like when I'm in state one, then this is the choice of like actions that I have. So maybe like according to this policy pi, that is like we represent it using the symbol pi. So according to this policy pi, this is the action I should be taking. So there are two types of policies. A very simple one is like deterministic, with meaning like there is one action mapped to one state. If I am in state S1, I should be performing action A1. Because maybe for that problem, I knew that like whenever I am, let's say, if the robot vacuum is stuck in that corner, there is like a deterministic thing, just like move towards the opposite direction because you're not able to move forward. Right? So that could be a deterministic policy. Always do that. So similarly, like if the robot vacuum is in the middle of the room, then there is this whole range of possibilities, right? So there is this whole distribution of actions that they can take. And so that's what we want to find out, which action to take so as to maximize my reward, right? So that's when stochastic policy comes in, like the distribution of actions that you have. And pi is nothing but like a conditional way of saying that if you're in state S, these are the actions that you can take. So it's like nothing but the probability of all these actions given a particular state, right? Just a distribution of all of them. So that's a stochastic policy. All right. So that's the second definition. We know what a model is. We know what a policy is. Then there is this reward signal. And you will come like this term reward will be used like interchangeably, reward and reward signal. Okay. And yeah, so we have a nice picture. I don't know how I forgot. So this is what's happening actually. I have my agent, right? Agent takes some action, A sub t, right? And then interacts with the environment. And the environment in returns changes the state, right? And it also gives it some reward. And this feedback, right? This feedback of reward and the current state my agent moves into will trigger the next course of action and so on, right? And like one thing that this agent will learn in this environment is that if I get reward for a particular action, maybe next time that is the action that I should be performing, right? Or maybe like a more complex case would be that instead, like in addition to reward, I'm also giving a penalty. It's totally up to you. So if I'm like penalizing my robot to get stuck somewhere, so it will try to not take that action in future. Okay. Okay. So going back to a reward signal. So the reward signal defines the goal in my reinforcement learning problem. I am taking some action, like from the perspective of my agent, I'm taking some action and I'm getting some reward. And so that reward is guiding my learning process in some ways, right? So in each time step, the environment sends to the reinforcement learning agent a single number or a reward. So one way of like, so at every time step, you will have something that's known as a reward. So that's like usually denoted by R sub t. So that's a numeric value that you're getting once you perform some action. It could like, it depends on how you model this interaction. It could be a negative, it could be a positive, it could be zero, depending on the action, right? So it's a numeric value. It's a signal that's sent back from the environment to my agent. All right, so that's reward. Now comes the most important part of any reinforcement learning problem, and that's known as the value function. Okay, so why is this value function so important? Well, if we think about the agent is not looking for an immediate reward only. It's trying to achieve some goal, and we said that it's trying to maximize all the rewards in the process of achieving that goal. So the value of a state is the total reward or the total amount of reward an agent can expect that will accumulate over the future. Okay, so starting from like whatever state you're in, you want to maximize this reward, and that's denoted by something that's known as a value function, right? And it's nothing but the expected discounted sum of future rewards under a particular policy. Okay, a lot of information, I know. So if we just like go back and look at like what's going on here, E is like the expectation for, so just like don't focus too much on policy yet, just like notice that there is a given policy pi, right? And my agent is in some state T, which is equal to S right now. So I have like these rewards at every time step, right? And we'll come to this gamma. So just like think of this gamma as some constant for now. It's a discount factor. I'll talk about it in detail. But just think that this is some other variable, right? And what I'm trying to do is I want to find the expected total value or expectation of the total reward that I'm going to get in like whatever number of time steps I'm looking at. So there are two things that come to your mind, like should come to your mind, like what happens here? Is this like a finite set of steps, right? Or is it like an infinite, like into the future up to what point are we looking at this, right? So there are two types of problems. There is one problem that's known as a finite horizon problem, where we are looking at some finite t steps. And there is this like continuous problem where we are looking at like infinite steps. And so there is a way to solve both of them. If we focus on the finite steps, that's what we're going to do today. If you focus on that, this is pretty easy to understand and translate to. But like we'll be focusing on this finite steps because it's easy to model, easy to understand, and easy to solve as well. But then there are ways to solve the infinite problem as well, right? So finite time steps, some examples could be I'm running my vacuum for cleaning this room. Then I just like turn it off and then I bring it back some other day, right? So it was like for a finite set of time that I run it, and then all the variables, all the state variables get reset to 0. Because again, I'm going to start it from the beginning. But then there are certain ongoing processes, let's say like an online system, customers are coming in, you're recommending items to them. So that's like a continuous process. And I don't know like in how many time steps I need to get calculate the value, maybe infinite time steps. So both problems exist. All right, so before we move on to formulating this problem, any questions or any doubts? People who are online, any questions before we move on? Okay, if there are, you can just like type in the chat window and we can. So until now, we haven't talked like anything that's hard to understand, but let's actually move on. There are some challenges with this overall approach, and I have like listed a few key challenges. We'll look at it in one of the later lectures. In the last lecture, we'll discuss them in detail, but I just wanted to still put them out here. Exploration versus exploitation. Agent only experiences what happens for the action it tries. So it may have to sacrifice reward in order to explore more. Like the agent was getting some reward right now, and they just like ignored it because they thought that they would like get more value later on. But then it's difficult to, and that's what the optimization problem needs to do. It has to balance both, right? So there are some challenges. And then the other challenge is how do we estimate whether it's a good model or not? Because we've had like metrics to do that in other I would say in other models, right? So obviously we estimate the expected rewards from a given policy, but then that has like some stochasticity involved. It's not as exact as we would like it to be, right? So some key challenges, control optimization, finding a good policy, and that's what the problem is. Like we need to find the best policy that might not be optimal in many cases. We are not able to, in most of the cases, we are not able to solve this problem optimally all the time because of a lot of constraints out there. Okay, So let's actually formally define this Markov rewards process. And why I'm calling it rewards process and not a decision process, because when I'm thinking of rewards, let's not think of the actions that the agent is taking. Let's just ignore the actions and think that what's happening is that there is this Markov process, right? So memoryless property exists for every state. And we are just like thinking that it's a finite set of states, and we are only interested in the overall rewards. I don't care about the actions, right? So this like reward signal that's passed from the environment to the agent is accumulated over all those finite time steps, right? So we want to accumulate that. And what we do here, so that's like goals and rewards. So everybody understands what rewards are, right? The positive that you're getting from the environment to the agent. And what we seek to maximize is the expected return. So here is something that we need to understand a little better. Now, this R sub t plus 1, R sub t plus 2, these are all rewards at each time steps. Okay. But then this is the future time step. So we don't exactly know the rewards also, right? So we have to bring in some level of stochasticity in some ways. And so what we look at is not this sum of rewards, but we look at a discounted sum of rewards, and then we come to the value function that is the expectation of this. So let me just write that down quickly. It won't take a lot of time. Okay, so instead of this, what we are looking at is that this G sub t, which is known as the return at time step t, right, is equal to our t plus 1, which is like the accumulation of all the rewards, right, plus a discount factor gamma, our t plus 2, plus the discount factor squared, our t plus 3, and so on. If this is like an infinite series, we can get the sum of this, right? We can get the sum of this infinite series. If it is a finite series, then we can also get the sum of this. So let's say it's a finite series, and I sum this up to some value t, right? And what happens is that I'll get something like this. T minus 1, k, or okay, so this is my like sum of expected returns if I have a finite horizon problem. Like let's say this is the vacuum problem and I know this is the number of time steps, right? And every run, by the way, and you'll come across this term as well. So sometimes you will come across this episodes thing. So episodes mean that like once I run it, once I run my vacuum for some like t steps, then I turn it off and then it goes back to its original state. And then again, I run it. So that's like one episode. And then the next episode is like when I run it again, right? So there can be some extra notation here. But the fact remains that what I'm trying to do is I'm trying to do something with these rewards, right? And then what is this gamma doing? Why is this like discount factor so important, and like why does it play a role? Well, these are like future steps, right? These are future steps. And so the value that I might get from doing something right now and getting some reward might not have the same value in the future. And so I have to take account of that. And that's what this gamma or the discount factor does, right? So as I think I have this, so it determines how much importance is given to your immediate reward versus the future rewards. And this could be an input parameter, this could come from your domain knowledge, but basically like the value is between 0 and 1 most of the times, right? So a value of 0 means you gave importance to just the immediate reward and nothing else, because like gamma starts to appear with the second term and so on. Right? Does that like make sense to everyone? Okay. So for example, like a discount factor, as I said, is giving importance to the immediate reward. A discount factor of 1. If I have a discount factor of 1, then what happens? What exactly are we looking at if I have a discount factor of 1? So what I'm doing is I'm giving equal importance to every time step in the future. And so this might go to infinity. So we have to have, because, right, I have a gamma, then gamma squared, and so on. So if we think of a value between 0 and 1, and let's say it was like 0.2. So that means I'm really like fading away the future steps quickly. If it was 0.8, then my future step, the value of my future steps is fading away, but not that quickly. So that's how this discount factor actually takes into account what I'm trying to achieve. Okay, so that's why this is important, and we shouldn't keep it as like 1. And like generally speaking, a reward received k times steps in the future is worth only gamma k minus 1 times, because if it was received immediately, I would have more value out of that, right? So that goes back to the definition of my value function. So I'm coming to the value function now. But before that, so we understand what Markov process is and what a value function is. But then when we are like looking at this returns function, my value function is defined a slightly in a different way. So let me just like quickly write that down, and then we'll be done with all of this. Yes, I'm not taking a break because we don't have a lot left, so I'd rather like finish this. Okay, so the value of state S under policy pi is the expected return when we are in state S and we are following some policy pi. Okay, so for example, like again, value, and we saw what a value function is. Think of that as like a sum of all the rewards that you get, right? So V sub pi for some S is the expectation of G sub t given state. So we saw what G is, right? The sum of all the rewards, the discounted sum of all the rewards. Okay. So if this is like the expectation, and if we just like break this term down a little bit, we can see, and like if I substitute the G sub t value here, so I'm not showing all of the steps here, we can tell that this comes down to something like this. So the expectation of r sub t plus 1 plus gamma times the summation of like k from 0 up to whatever that t value was, and r t plus k plus 2 given s t equals s. You don't have to remember all this. Why I split it up is because I wanted to show you that there are these two terms that the value function is comprised of. Like the two important components of my value function are these: the expectation of my immediate reward that I get when I'm moving from S to ST plus 1, right? And the discounted sum of all the rewards in my future, right? So this is good because it in some ways is like a recursive relationship between a value that I'm getting right now and the value that I'll get by like getting rewards in the future. So if I like really try to simplify all of this, I can rewrite this thing as, and I think this is the heart of any Markov decision process. If you understand that this is how the value function is defined, that's all there is to like your problem solving. You won't have issues like understanding this next time. So that's why I'm emphasizing too much on that. Maybe you don't remember the rest of the definitions, that's fine. But remember the value equation, right? This how the value is computed. And if you like remember that, that's all we need. So basically, if you remember from the definition, the value is like how good it is for the agent to be in state S, and that is equal to the expectation of the reward it's getting by leaving its current state, plus the value of the state it has moved to, right? So maybe I can write this thing as the expectation of RT plus 1 plus gamma stays as it is. This here is nothing but this V pi S again, but in like T plus 1 in the future, right? So what we can write here is that this is V pi S plus 1 given S sub t equals S. Right, so that's how this is recursive, because here basically the value at step S is the reward, the expectation of the reward, plus some discount factor times the value in my next step, and so on. Right? Yes. Yeah, I think I removed, like I said, ST is S. Yeah, to make things easier. Yeah, but S is like S sub T. And then where I'm saying S plus 1, it's like ST plus 1. Yeah, just to make, so because there's too much notation. Yeah, and I think I mentioned somewhere in the notes. Like, does that make sense to everyone? Like, I know I still have like t+1. I'm going to get rid of that as well. So I know that's confusing. Yeah. So basically, again, like I'm repeating, the gist of this entire Markov decision process lies in this value equation. And remember, my assumption was that I don't care about my actions. I'm only thinking about my rewards at this point. I'm only thinking about my rewards. I will bring actions in some time. But to make it simple, let's like, and this is, by the way, known as Markov reward process. So the Markov decision process is derived using this because there isn't much to it beyond this point. Okay, so once we have this entire thing, we talked about something that's known as the transition probability earlier, right? It was the probability of moving from one state to another, right? And we would need like, because we are moving from one state to another, we would like, if we just get the expectation of this value here, like the value in step t+1, we would need that probability to come in, right? Because the expectation is what? The actual value times the probability value, right? So again, I'm not deriving each and everything, but because we know the definition of the probability of moving from one state to another, and so we can make this equation even simpler, this value equation. And let me write that down again. And by the way, the resource that I've provided has like the entire derivation, but I'm just focusing on things that you need to know, right? So if I make this like really simple, and I'm even removing pi to make things understandable, we are really looking at the reward that I get when I move out of time step S, right? Plus the discount factor gamma, right? And the sum of like all the state movements that I did. And this is the transition probability of moving from S to S prime, right? And then the value that I have at S prime. Okay, so why this? Because remember, like when we formulated this first, it was an expectation. So I've removed that expectation now, and that's why I brought in the probability value, right? And we defined this transition probability earlier. Let me rewrite it. I think we have it here. So this is the transition probability, the probability of like moving from state, moving to state S prime and getting a reward R, given that currently I'm in state S and I have performed some action, right? So usually from my domain knowledge, these transition probabilities are known, or I'm able, like enough information is there so that I'm able to compute these. Okay, so this was a side note, of course. Now, if we just look at this equation, just this equation, this value equation, I can like further simplify this to solve for my VS, right? And if I like just substitute for like call this P, right? And then make some rearrangement of terms because this V, let's say the like S and S prime are the same, Markov, right? That my state depends on my, like it does not depend on my history, but it depends on like my current. That was my future. And so in matrix form, I can, based on a lot of assumptions, simplify this a lot. So I can like get some kind of an equation, like this is the identity matrix, this is the transition probabilities, so these are transition probabilities inverse the return, the overall return. So I am able to come down to this equation if I just rearrange the terms and solve for my V. So basically, I'm trying to compute this V. I'm trying to find out what is my value given like my agent and my environment and the rewards that I'm getting. And you can analytically solve this equation because this is like all the matrix of transition probabilities is a matrix. Because like, let's say there were n states. So you will have like probability of moving from state 1 given state 1, probability of going from state 1 given state 2, and similarly a probability of moving 2 given S1 and so on. Like let's say you have n states and so on n states, right? So this is the entire like matrix, right? And this is like the identity function. Reward is usually like a one-dimensional vector, depending on like different, like when you got a reward or when you like ones or zeros or like -1 or whatever. And then you're able to solve this. You can analytically solve this. So now the issue is that the runtime complexity when we try to solve this is like really bad, and it takes a lot of time if it's a very long process, because you have like a lot of these transition probabilities. Because let's say if I had like n like transition states, and n was like some 1000, and so like and 1000 is nothing, you can have like even bigger number of states. This becomes difficult to solve, right? So it's not a good solution. So next time what we'll see is some dynamic programming methods and some ways to solving this equation. And this equation, by the way, is known as the Bellman equation. So if you ever come across that term, you know that we are talking about this value equation, right? So like everything in a Markov reward process comes down to solving this Bellman equation for my value. And high level, even before we start solving it, I just wanted to let you know that finally, in a reinforcement learning problem, we are trying to find that best policy that maximizes my value. That's the optimization problem that I'm trying to solve. So we'll see next time how to do that. But one quick thing that I still wanted to add, because all of this that I explained just now was the Markov reward process, because we were only focused on rewards. Now, if we bring in something that's like, if we bring in actions as well, right? Because in every state, the agent is taking some actions, right? So then that is known as a Markov decision process, right? So as I have like stated here, so a Markov decision process would be the Markov reward process that we just saw, plus the actions. So nothing changes again here, except that the conditional, like the expectation over the conditional, will have like the set of actions as well. So let me write that equation down, and it's known as like sometimes the Q equation, or the Q value that you must have seen if you ever came across reinforcement learning. So let me just write it down. So eventually what we are looking at is like the value of taking action A when in state S under policy pi. Okay, so then policy is, let's say, some pi. We'll talk more about it next time. State A, and there is an action as well. So it's the exact same value equation, except that my expectation, let me write it down, of my G sub T, remember my returns, is not just condition on my state, but also like on my action A. That's the only thing that gets added. The rest of like the assumption that it's a Markov process from state to state stays the same. And we'll see like how we can also show that this decomposes into something. And then we are really looking for a policy pi that like maximizes this value, and not just like that V value that we saw, but still it has the same form. But because you will see this like Q value a lot in reinforcement learning papers and otherwise in literature. So it's nothing but the value function, but it's also like it includes the actions of my agent, right? So that's like the fundamental idea behind formulating a reinforcement learning problem as a Markov decision process, right? It makes my life easier, and it has a very nice recursive form that can be solved using a lot of different approaches. Dynamic programming is one of them. We'll look at it like next time. But here, if you look at this MDP and you look at other research papers, you see that MDP is defined by like SAPR and this gamma. So whenever you see SAP or gamma, that's all you have to specify, and you know that this is how your model is, right? You have to specify S is a finite set of Markov states. What are those finite set of states? Finite set of actions. P is the model that's so this is like calculating the transition probability. Do you have a model, or is it given? Like whatever, I don't know. R is the reward function, and gamma is the discount factor. So if you have those 5 things, you can define your complete Markov decision process and then model a reinforcement learning problem. Okay. All right. So that's all I wanted to discuss today. So we talked about basic building blocks of Markov decision process today, right? And next we'll talk about the Bellman expectation equation. You saw that equation, but now we need to come up with the best, right? But the best policy that gives me the maximized value of that value, the value function. So that's what we're going to look at. And I'll talk more about what is an optimal policy, optimal value function, And what are some of the ways of solving that? We saw one way of solving it like analytically, but that's a very inefficient way. It's good to just express it that way, but solving it like that is not a good like solution. So that's all that I have. I'd highly recommend going to this source and looking at this book, and maybe just like keep it for now. You don't have to read it right away, but this is like a very like comprehensive book that talks about like reinforcement learning problem and all different like methods that are there to formulate the reinforcement learning problem and solve it. So multi-arm bandits, and I hope to cover that. Most likely I will try to cover that. And we looked at finite Markov decision process today, right? And then it talks about dynamic programming, Monte Carlo methods, and other techniques as well. So if in future you're interested, you can refer to this one. So just like keeping that, like save it somewhere. It's a good resource. All right, so that's all I have for today. Any questions before we end? All right, so next time we are going to look at like how do we come up with that optimal policy that we were talking about, right? And what are some of the good ways of like getting that? All right, so thank you everyone. And yeah, one thing, by the way, I forgot